Assalamu alaikum. Now, today's lecture actually mainly is made for discussing questions on half-life, but here we will begin with the nature of radioactive decay. So what is radioactive decay? Actually, it is the emission of energy or radiation in the form of ionizing radiations. These ionizing radiations may be alpha, beta, or gamma. So there are three types of radiations which are emitted from unstable nucleus. What is meant by unstable nucleus? That is the atom which has atomic number more than 82, equal to or more than 82. But there are some radioactive nuclei which have atomic number less than 82 also, and they have various uses in the field of medicine and industry, etc. So here we will just have a brief overview on the types of decay. Alpha decay actually is emission of alpha particle. What is alpha particle? Helium nucleus. As the formula is seen, that is, it has 2 protons and 2 neutrons. So it's Z, that is atomic number is 2, and nucleon number 2 plus 2, 4. It has 2 protons, 2 neutrons. Okay, so whichever atom undergoes alpha decay, its A decreases by 4. A is nucleon number, that is proton plus neutron, and Z is proton number, that is an identity of an atom. Okay, because any atom is identified by its number of protons. So whenever any atom nucleus undergoes alpha decay, its identity completely changes. Okay, so it does not remain the same atom anymore because it has now 2 protons less than before, right? So alpha decay causes A to decrease by 4 and Z to decrease by 2. In the same way, beta decay is emission of electron. So electron does not reside in the nucleus of an atom. From where does this electron come then? This electron actually is emitted due to the decay of neutron. So what happens in decay of neutron actually? That this neutron actually decays. Suppose an atom has, say, 236. 236A. What does that mean? Proton plus neutron is 236. Okay, and its Z is, say, 92. 92 protons are there. So if it undergoes a beta decay, means one neutron splits up into one proton and one electron. So electron cannot reside in the nucleus, so it emits out as beta particle. So this is beta, and what is the symbol for beta? -1, that is a charge, and it has almost no mass. So this is the symbol for beta. And what happens to this proton? That will be added, that will remain in the nucleus. So due to splitting up of the neutron, what happens? A is P plus N. So one neutron has decayed, but one proton is added up. So P is added up and N is decreased by 1 because one neutron has decayed. It has become proton. So it means that Z will remain 230, A will remain 236. And since due to addition of one proton, Z will become 93. Okay, so what will be the daughter now? Suppose X, how do we represent? 92 and 236. So as a result of alpha decay, what will happen? Beta decay. Beta will be emitted, and that atom is no more the same atom because its proton are now different. So it is 93, and that will remain 236. Okay, so as a result of other decays, gamma decay. Gamma decay is emission of electromagnetic radiations. So they don't have any charge or mass. So identity of atom does not change. Identity of atom does not change. And gamma is actually electromagnetic radiation without any charge or mass. So the atom will remain the same. Okay, so actually this happens usually after alpha and beta decay. Mm. Now let us have some more discussion on nature of radioactive decay. Nature of radioactive decay, it's a random process. It means we cannot predict which atom will decay when. Okay, when will a particular atom decay and which atom will be that one which is going to decay now. Which atom will decay now or when will a particular atom decay. So it means it's randomness due to space and time. And in the same way, radioactive decay is spontaneous. Spontaneous means we cannot cause influence or influence the decay. So if you apply pressure, if you increase the temperature or any chemical reaction will not change the behavior of this decay. Okay, so it's both spontaneous and random. Okay, so here the factors are written which will not change the rate of decay. Whatever number of nuclei are decayed per unit time, that will not be changed due to this. A random process is defined as, that is, the exact time of decay of nucleus cannot be predicted. In the same way, we cannot tell which atom will decay now. Now, the graph which shows the half-life is a spontaneous graph, that is count rate, which decays exponentially with time. But this is not a smooth curve. This smooth is the curve is not smooth because the process is random. Okay, because it means the number of atoms which are decaying per unit time, it does not remain same, it will be fluctuating. Suppose in first 10 minutes the atoms, suppose initially an atom has 400 atoms, and half life is what, the time in which the amount of this decay rate decreases to half of its initial value. Half of initial value means 200. So it means suppose half life is 10 minutes. So in 10 minutes from 400, the atoms will remain only 200. So 200 means it is not exactly 200. It may be 199. It may be 203, 204. There will be little fluctuation. And the next 10 minutes, it will not be, it may be exactly 100 or it may be slightly above or below 100. So that is why there are some fluctuations in the count rate with respect to time. So how do you study the nature of radioactive, random nature of radioactive decay? You have to use a GM tube, and GM tube has to be placed near the source, and we have to record the decay count rate at regular interval. The interval depends on the half-life. We have discussed about the half-life in the previous video. That is the time in which half of the atoms in a sample of radioactive atoms decay. So that time actually is known to us, and that is particular for particular radioactive nucleus. It may be 10 days, it may be 100 years, it may be seconds. Okay, so in order to study the random nature, we record the count rate at particular intervals like 10 minutes or 5 minutes or maybe 1 2 minutes if the half-life is shorter. Okay, and then graph is plotted, and we will see that we're not getting exactly the same decrease in the decay for same interval. Okay, so there will be little fluctuations. Now we will solve some questions related to nuclear, that is half-life. So here, this is a question. The nuclear equation below shows a decay of plutonium nucleus to an americium nucleus. So here the equation is given and it is decaying beta particle. Okay, and you have to write the quantity that is represented by letter Z. Letter Z is proton number or atomic number. So this atomic number, what it will be? Since this has undergone beta decay, means Z would be 94. Due to result of beta decay, Z increases by 1. It has become 95, and it means before undergoing the decay, it will be 94. Okay, then there's another question. The americium nucleus decays by emission of the alpha particles. It means this is also not stable. Okay, and that also decays, and it undergoes alpha decay. So you have to write down the nuclear equation for this decay. So, and you remember that due to alpha decay, Z decreases by 2 and A decreases by 4. So what will be the equation? Let us see. And they have given the daughter. Daughter is neptunium. Neptunium, due to decay of alpha particle, this will Z will decrease by 2, means it is 93, and A will decrease by 4. So it means 241 minus 4 is 237, and this is alpha particle. Okay, so this is the equation which indicates that alpha decay of neptunium. Okay, now there is a question. The half-life of this americium nuclide is 470 years. Okay, and the sample contains 8 into 10 to the power 14 atoms in the beginning. At t equals to 0, how many atoms are present? 8 into 10 to the power 14. So after some time, this decreases to 6 into 10 raised to the power 14. So what will be, calculate the time required for this decay to occur. So what we will have to do, we are interested in these types of calculation, we are interested in the number of atoms which are remained. Number of atoms which are remained means number of atoms which are remained. What we will do, how many nuclei were initially present? 8 into 10 raised to the power 14. 8 into 10 raised to the power 14. They were present in the beginning at t equals to 0. And after some time, how many have decayed? Decayed 6 into 10 raised to the power 14 have decayed after some time. Okay, so how many are remained? So we will take the remained. We will subtract from the nuclei which were present at t equals to 0. 8 into 10 raised to the power 14 minus 6 into 10 raised to the power 14. That will be 2 into 10 raised to the power which are remained. So the formula will be what? The fraction remained is, what is the half-life given? 470 years. Half-life is 470 years. Okay, and remained is equal to, this is the very famous formula, n is the number of half-lives. How many half-life have passed into n which was initially present. If we know the half-life, number of half-life, we can use this formula. But here we don't know how many half-life have passed in that time. So how can we get this value of n? We will check. From 8 into 10 raised to the power 14, what is half? 4 into 10 raised to the power 14. One half-life has gone. In another half-life, 2 into 10 raised to the power 14 atoms. So they are remained. Okay, so how many half-lives are there? 1 plus 1, 2 half-lives. Okay, so 1 half-life is 470. So 2 half-lives means we will multiply it by 2. Okay, so the answer will be 940. 2 half-lives, and 417 into is 940 years. Okay, so there is another question. A radioactive source is placed near a detector connected to a counter. 200 counts are recorded by the counter in 3 minutes. The background count rate is 20 counts per minute is the corrected count rate for the radioactive source. Okay, so what you have to find out, there is some missing part in the question. Anyhow, you have to find out what will be the corrected count rate. Okay, and after actually corrected count you have to find out. So 200 counts are recorded in 3 minutes. And what is background count? 20 counts per minute. So here this is 3 minutes. The total count, 200 counts in 3 minutes. So what are the total counts in 1 minute? Because background counts unit is counts per minute. So what we will do, first we will find out the count rate per minute. So 200 counts in 3 minutes. So how many counts in 1 minute? Will be 210 divided by 3. So that is 270 counts. And this includes background counts also. Okay, so there are 20 counts per minute. So 70 minus 20 is 50. Corrected count you were supposed to find out. So that was 50 counts. So you have to subtract the background counts from this. Okay, now let us go to next question. So answer is A. Question number 3, this is the graph. And the graph shows how the count rate measured by a radioactivity detector placed near a radioactive sample changed with time. So this is exponential decay again. And background count rate is 30 counts per minute. So what is the half-life of this sample? So what is the procedure? First, this is the total count, 530. If you see the graph, that is clearly seen. There are 5 divisions between 550. 550 means each small division represents 10. So 510, 20, and 530 is the count rate at t equals to 0. So half-life means what is half of 5? First, you subtract the background count from 530. So 530 minus 30 is 500. Okay, so 530 and we subtract actual count is now 500. So at t equals to 0, actual counts which were observed were 50 counts per minute. Okay, so one half-life, it means what is half of 500? 250. So 250 and 250, because the graph is plotted by taking count rate, total count rate means background counts are included in this. So you have to again add after dividing it into 2, that is taking half of 500 because you are finding out one half-life. Okay, so 500 divided by 2 gives you 250 and add 30 counts per minute back to it. So that is 280. So 280 here is coming 250, 260, 270, 280. And what is the time here? 3.2, 3.4. It is the fourth block, second block. Each block represents 0.2. Okay, so that was the previous the question in which half-life is 3.4. So answer will be A. Now, question number 4, the half-life of a radioactive isotope is 2.5 minutes. This isotope is only radioactive isotope in a radioactive sample. Between time t equals to 0 and t equals to 7.5 minutes. This is a total time, t equals to 0 and 7.5 minutes. The mass of this isotope is the sample decreased by in the sample decreased by 70. It means it is 70 microgram less than whatever it was in the beginning. What was the mass of these isotopes in the beginning? That is t equal to 0. Okay, so total time is given 7.5 minutes and half-life is also given. So we can find out half-life, number of half-lives by using the formula. Here, what is happening? 7.5 divided by 2.5. So what do we get? 3. It means 3 half-lives have passed. And in the beginning, what was present at t equals to 0? We don't know. We don't know how many nuclei were present in the beginning. So we can write t equals to 0 and we don't know the mass in the beginning, m0. We don't know it. But after 3 half-lives, that is how much is remained? That is 70 microgram less than before. Okay, so in 3 half-lives, fraction remained. I gave you atom remained. We can calculate it using this. Atom remained is equal to this formula was just given for the other question also. That is half raised to the power n. Okay, into number of or mass initially present. Now, let us have a look at the question. Fraction remained 70 microgram. Decreases by 70 microgram. So remained is what? M nu minus 70. It is 70 microgram less. Let us go back to the work here. So M minus 70 is equal to half. What will write in place of N? There, how many half-lives have passed? 3 half-lives have passed into mass which was initially present. We can write M0 at t equals to 0. So this is the new mass and we can write what? M equals to M minus 70 is equal to 1 over 8 into M0. Okay, so this is remained, that is M0 minus 70. Okay, so we can bring this M0 to this side. M minus M0 divided by 8. Because 1 upon 8 into M0. So this is brought to this side and that becomes negative is equal to 70 goes to that side. Okay, so that is 7 m naught by 8. 8m minus 8m naught minus m naught divided by 8 is 7m naught is equal to 70. So what is m naught? The mass which was initially present at t equals to 0 is 70 into 8 divided by 7. So 7 tens are 70. 80 microgram were initially present. The answer is B. Okay. Now next question. The half-life of zinc 71 is 2.4 minutes. If one had 100 gram at the beginning, how many grams would be left after 7.2 minutes? Okay, when this time is elapsed, how many half-life period have passed? Total time, this is another formula which you should know. What is that formula? That is total time divided by half-life. So 7.2 divided by 2. 2.4 is 3 half-lives. So 1 upon 2 raised to the power n, 1 upon 2 raised to the power 3 gives you this, or you may write 1 upon 8. Okay, 100 into 1 upon 8 gives you 12.5 gram, which is remained. Now, question number 6, a radioactive isotope of sodium has a half-life of 15 hours. The table gives the data from an experiment to show how the rate of decay of the isotope varies with time. The background count rate has not been subtracted. It means this is giving the uncorrected count. When we subtract background count, we call it corrected count. Okay, so this is uncorrected count, total count, which includes background. At t equals to 0, what was the reading? 400. And it includes background as well. All the readings have background in it, and we have to find that out. Okay, and what is the half-life? This is 15 hours. So total time which is given here is 30 hours. Okay, it means how many half-lives would be there in this 30 hours? 2 half-lives. 1 half-life 15, 30 hours means 2 half-lives are there. So we can find out the background count by applying the logic here. What will be the logic? We will write remained equals to, I'm writing R, okay, half, and we know how many half-lives are there? 2. N into initially what was present in the beginning. What was present in the beginning at t equals to 0? There were 400, and that includes the background count. At t equals to 0, actual count is at t equals to 0, 400 minus B. Okay, background is to be subtracted to know the actual count. And at t equals to 30, what was the count present? That was 115. So 115 minus B. Okay. So what is the fraction remained? Actual count in the beginning and fraction atoms, not a fraction, atom remains after 30 hours is 150 in minus background. This B represents here background. So we will write 115 minus B equals to 1 upon 2 power. What is how many half-lives are there? 2 half-lives into 400 minus background into actual count. We can write initially count at N0. So 400 minus B, 115 minus B. So this is 1 upon 4. And this is 400 minus B. 115 minus B. So if you take 4 to this side, 4, 115 minus B is equal to 400 minus B. So 400 into 115 is 460 minus 4B equals to 400 minus B. We can keep similar variables at the same side. So 4B goes there, becomes positive, and 400 comes here. 460 minus 400 equals to 4B, which has become positive now, minus B. So here we will do next calculation here. 460 minus 460 is equal to 3B. So B will be 60 divided by 3, 20. So 20 counts for background counts. Okay, so answer is C. Now, carbon dating. This is another application of nuclear radiations. So, due to cosmic rays which enter the atmosphere, they convert nitrogen-14 into carbon-14. Okay, and living organisms are constantly incorporating this carbon-14 into their bodies along with the carbon isotopes. Like along with the carbon-12, they absorb carbon-14 also till they are alive. Okay, when the organism dies, it stops, of course, absorbing carbon-14 anymore. And the old carbon-14, because it is radioactive, so it keeps decaying. Okay, but when the plant or living organism, when it was alive, it was absorbing also, the ratio was same. Carbon-12 and carbon-14, the ratio was same. But after the plant decays or living organism decays, it does not absorb carbon-14 anymore. Okay, so that is why this amount of carbon-14 keeps on decreasing. So that can be monitored. And carbon-14 is having very long half-life. It is around 5,730 years. But you may call it around 5,730 years. Okay, so when we observe this half-life, see here, this is nitrogen 14, which becomes carbon 14. Okay, due to the cosmic radiation, plants absorb it, and the ratio of carbon-12 and carbon-14, usually it remains same till the organism is alive. When organism dies, it does not absorb carbon-14 anymore, so the amount of carbon-14 keeps on decreasing. So how can we calculate the amount or a half-life, the age of dead organic matter using this? We need to know the amount of radiation. So suppose a plant, we get any plant, the sample of a plant which is supposed used to make furniture. So, okay, one piece of furniture is taken from oak tree. Okay, and that is old. Okay, a piece from a furniture or piece which is cut from any dead plant, and we note down using the GM tube. Suppose this is the piece. We use GM tube to monitor. We record the count rate. Okay, so this is because count rate which is given half-life is 5,730 years, but that may be slightly different in different sources. You can get either 5,500 or something like that. So this is oak tree and this is GMTU and this is counter. We record the count. Suppose this sample gives count rate of 4 counts per minute. Okay, Okay, so now what do? We find the same type of plant and same quantity. Okay, so that it is a fair test. Same, but from the fresh plant. We take fresh plant and same mass of that fresh plant is taken and same type. Okay, because that number of carbon 12 atom and carbon 14 atom, that will be different in different masses and different types also, that may be different. Okay, so fresh plant, we take the same mass and we monitor. Same mass and type. And we again do the same thing. Now we replace this old with fresh. And of course, it is fresh. So it has more number of carbon 14 atom present in it. The old one, because carbon 14 had been decayed, so amount was less, and decay rate depends upon the number of nuclei initially present. So old plant has had smaller number of carbon 14 in that piece, and that was giving only 4 pounds. And fresh, same amount is taken, same quantity is taken, but it is giving more reading. Suppose it is giving 32 counts per minute, because there are more carbon 14 atoms. So that means the decay rate is also more. So first we find out how many half-lives have passed. Okay, so we can get what? We can take half of 32. What is half of 32? 16. How many half-lives have passed in dropping from 32 to 16? 1. 16 to this, what is half of 16? 8. Then 4. So 3 half-lives have passed. If it is even older plant, we might get 2 counts rate also. Okay, so 3 half-lives. So fraction remained equals to half n into atoms present. But do we need this formula here? No. We have to find out how long does it take, like how much older the old plant is. Suppose you have to find out how much older the whole old plant is. How many half-lives have passed? 3 half-lives have passed. So 1 half-life, 5,730 years. So what will be the total time when that old piece was the part of fresh living plant? Okay, so you will multiply number of half-life by 1 half-life time, and that will be, let us see what comes, 5,730 into 3. So that is 117,190. Okay, 17,190 years have gone. Okay, that was the piece of fresh plant, and it has had been decayed 17,190 years ago. Okay, so this is the end of the topic, and we will discuss some more questions in the next video regarding the topic.